Hi everyone, this is Mahesh. Hope you are doing good. This is a continuation of the previous video where we are looking into the asymptotic analysis, and in this video we will see how we have to do the big O analysis for different kinds of loops if else statements. So first let us consider the loop, for loop basically. So if we consider, say for example, for I equal to 1, I less than or equal to n, I plus plus, then we execute some statements here. So this statement is basically of order n square, n. So how this one we have already seen in previous videos. So where this particular statement execute for n times. So its total running time will be n. This will be our f of n. So this is, when we write it in Big O notation, this is nothing but order of n. So this is for normal for loops. Now let us consider the second category, which is nested one. So in that case there will be one more for loop inside for loop for j equal to 1, j less than or equal to n, j plus plus, and a statement gets executed here. Okay, so basically this execute for n times, this execute for n times, this statement executes for n square times. So overall it is n square plus 2n. We can simply write it as fn equal to n square plus 2n, that is nothing but order of n square. Why? Because we only consider the maximum contributing term in this particular polynomial equation, that is n square here. So it is of order n square. Now in the next category we will see how the consecutive statements occur, or how the consecutive statements execute. So for that, let me make it a little bit small. For I equal to maybe 1, I less than or equal to n, I plus plus, statement 1 executes here. Then after that we have again one more loop, I equal to 1, I less than or equal to n, I plus plus. This time it is a nested one for j equal to 1, j is less than or equal to n, j plus plus, and statement 2 executes here. So this is basically consecutive for loops. So one is a normal single for loop and another one is nested, which executes one after the other. So we know this executes for n time, and let's ignore these two terms. Let us only consider this one. This executes n square number of times. So we can write f of n equal to n square plus n here. So this is our time function. So if that is the case, then it is of order n square. It is of order n square. It is still of order n square because that is the worst case for this particular statement's execution. Now let us consider if else statement. So I will remove this. So let us say if condition 1, then statement 1 executes, else if that is not the case, we read this particular loop executes statement 2. So if you see, this is of order 1 because it's a single statement. If this condition is true, then only this statement executes for one time. So for that reason, this is order of 1. But if this condition doesn't satisfies, then it will come to this else block. This executes for order of n time. So out of these two, which one is bigger one? This is the bigger one. So if we consider worst case, because we don't know whether this condition satisfies or no, in the worst case, if it doesn't satisfy, then it executes this particular statement. So whatever is maximum out of these two, we will have to consider that. So that's why the order of this particular statement is order of n. So this is basically the linear running time. So basically, as the input grows, the running time also grows linearly. Next one is logarithmic running time. So this logarithmic running time, this occurs normally when here in the earlier for loops, what was happening, I was growing like one after the other, means it was incrementing by 1 on each iteration. But here if at all the I gets multiplied by some number, then that time this particular logarithmic time complexity, we can see that here. Let us take an example for I equal to 1, I less than or equal to n. Here I equal to I star 2. Say for example, every time I gets incremented by 2. So how to analyze this one? Let us see. We will take I value when I is 1. Initially I was 1. So next it gets multiplied by 2. So it becomes 2. In the next iteration, it will be multiplied by one more 2. So we can write it as 2 square. So this one we can simply write it as 2 raised to 0, 2 raised to 1. And this continues until I becomes less than or I becomes equal to n value. So once the I value becomes greater than n, that time it stops. So we don't know how many number of iterations it will execute. Let us assume it executed for k times. So it is 2 raised to k. So when it will stop? When 2 raised to k becomes greater than n, that time this particular loop stops. So if we apply log on both sides, it becomes log 2 to the power k greater than, let us assume when it became equal to n, it stops, and it is log n. So it is k equal to, if we apply to the base 2, this term becomes 1. So into 1, it is log n to the base 2. So k is equal to log n. So this term is of order log n. So this is basically how we analyze logarithmic time complexity. So if it gets incremented by 2, it is of order log n 2. If it gets incremented by 3, it is of order log n 3. Likewise, it continues for whatever value this I gets incremented, the base of this logarithmic value takes place with that particular multiplier here. So that's how we normally analyze the time complexity for different loops, different if-else statements. That's it in this video. We will understand further more examples in the upcoming videos. Thanks for watching.